Okay, so you can start, Flavio, I think.
Okay, then thank you, Alexander. So I will start. Today I talk about, I should have said possible experimental consequences, not experimental consequences, because there are not many experiments that work with Axion electrodynamics. One of the reasons to tell about this topic because we started doing this here on years ago, more than 10 years ago. And it does help to give a starting point for PhD students of some Ukrainians who came at the time of the program Ukratop, which now is the Burkumat program. There are other programs that appear since the Ukratop program stopped in 2022. And it's just actually that was very good for at least for the theory. The part of most of the students in the FW were going to experimental physics at the time, but got some students, and I was very happy to finally meet some people who can teach me something. So then I have the first. Since 2021, this year I can say I have a kind of a personal milestone that for me, I counted 10 papers with young Ukrainians. So since 2021, right? This is the first part of my talk has little to do with actual electrodynamics, but this is our, this is she's there, Vera. Vera Shita, yeah, this is a very much used photo and presentations Ukratop. This we took this photo during all discussions, which in her case, she started actually with axial electrodynamics, but you move her to something else, and then she went back to electrodynamics at the end of her PhD. Her PhD is quite singular because it was literally, it is, I mean seriously, literally written here. It was literally everything written. So there are thousands of blackboards done during her PhD. That was seriously, well, I will show you. This is Edward Nychuk, who came a little bit later. Still before the full-scale invasion started. And then more recently, we saw her in Lviv workshop, those who were present there, Anastasia Chizhikova, who we showed in this Lviv workshop her results for her master's, actually. Now she just started a PhD, right? So nine of these 10 papers I mentioned came from these three people. The paper number 10 is from postdoc Svetlana Kondovich. And this was, I will briefly show this is the thesis of Vera, which I must say, but this was the last paper from her PhD. And it's interesting that when I say that was literally done on the blackboard, these three papers, these three first papers, there are two physical review letters here. They don't have any figure. They are pure theoretical based mathematical formulas that were written in the blackboard. They came to the papers. Here there are figures. Those papers don't have figures. Those papers will have some figures. This was her PhD, essentially. I'm happy that we're still now she's postdoc at the Max Planck Institute. She defended successfully her thesis with the highest grade, summa cum laude, got a medal. We got a medal, right? So got a medal from Leibniz Institute to give a medal to best student, right? So and then this is Edward who submitted his thesis now. Edward just submitted his thesis. This is also very theoretical work. You see, the topics are very diverse. This is no emission quantum filter. That he's doing. It's a very diverse topics, right? So that's and here Svetlana is ferroelectrics. But she's not a PhD student. That's ferroelectrics. This is more recently, so it's collaboration with Asli Sudbo, who you saw. He attended last year your workshop, and you saw him also this year in Lviv. And finally, Nastya, okay, that's Axion. She used Axion electrodynamics. So this is a paper who was her master's. Actually. This was editor's suggestions in Physical Review B. Was accepted immediately, practically immediately, very smoothly. And now, after this introduction, which is just about saying how happy I was to meet those people that came from here. Thank you that you sent them to us. really happy about that. And now we can start the topic of this talk. There are some papers, the two last papers in Vera's thesis concerns Axion electrodynamics. This is a part, that's the second part of the talk. But I want to start very simple. The second part, for the time's sake, I will not have time. I want to explain better the first part because it's very simple, really. The only thing you need to know is your second semester or third semester. I don't know how it is here, but electromagnetism. Okay, just see if you look only this part of the Lagrangian, this is an insulator, right? That's a dielectric. If you forget all the three last terms, right? That's the Lagrangian quantity. If you add the two last terms, that's just the Lagrangian electromagnetism that you learn in textbooks. There is nothing quantum mechanically between these terms, these terms, and this term. This is the electric potential, this is the vector potential, this is the current, this is charge density. And the only term that you don't see is here, which is a term which is called by several names. The magnetoelectric term, because it mixes electric and magnetic fields. In the way it's written here, this is a term that has topological properties. We'll see a little bit about this. For the moment, you believe me, meaning that is independent of the metric, but also because generally in topological materials, this theta is a constant that is quantized. The only quantum object in this Lagrangian, you see that diverts from what you see in classical electromagnetism textbooks is this term. Because this alpha is the fine structure constant. It contains h bar. In Gaussian unities here. E square over h bar c. That's the only quantum element. So in some senses, this equation is semi-classical. Okay? This is semi-classical equation, which means, okay, I can study this in several geometries. Let's see if what theoreticians predict makes sense, right? Mostly doesn't, but well, because materials are much more sophisticated. Materials are much more complicated in the mind of the theoretician. Theoreticians are very simple-minded person who thinks that the three-dimensional space is infinite. The boundaries are flat, see, or something like that.
Flavio,
yes.
Sorry, I missed it. How you explain? But
yes.
Have you explained how this term appeared?
Well, this term for the moment I just put it there. This term comes actually how it appears. It appears in several ways, right? So originally it came from high energy physics, right? There was this people concerned with charge parity violation, etc. But there has some various names depending on whether this is constant or not. Actually, more accurate, we say Axion electrodynamics. This is also field, has a dynamics. But for this talk, it will not have intrinsic dynamics, right? That will be not a scalar field. This will be for us, most of the talk is constant. Second part of the talk is not a constant, but it's not dynamical in the sense that there is a classical field equation for that. So what I said that your question where this comes from is, for example, in topological insulators, this term is there because of spin momentum locking, because electrons on the surface, on the boundaries, on the topological insulator, spin up goes the same direction of momentum plus k. The spin down follows momentum minus k. This creates some orbital motions that could go on the surface, that when you go to the edge, reflects on a term like this. It can be derived explicitly. Right? It can be derived explicitly from microscopic models. And the question is this, there are many things you can predict with that, because everything here is familiar except this term. Of course, there are magnetoelectric terms that appear in both ferroite materials, but they are much more complicated. They are not topological. It's not saying the problem is many talks we give. It looks like this term is something that appeared first time recently. No, in condensed matter physics, it's not true. There are engineers who consider very complicated things. I saw once a guy published something in a journal I didn't know it exists, called Marconi Review, about antennas. You see, he had mixing he had magnetoelectric terms. It is mentioned also in
but this goes to, let's say, kinetic term of how it's.
no, this is actually no, this is
No, you are right. Actually, this is a kinetic term if theta is constant. Right.
yeah. Kinetic with sets, let's say.
Yeah, kinetic actually, quadratic. Basically quadratic. Yeah.
It actually is just in this sense. Yeah, it's a quadratic term. This sense is a quadratic term, but in reality, this is a total derivative. You will see why. Let's say there's a total derivative, but it has consequences. If theta is constant, there's a total derivative. You know from classical mechanics, total derivatives in the action.
No, actually, it's
appear,
easy to see why Flavio actually speaks about topological insulator, because it's actually total derivative. If theta constant, then it means nothing for the dynamics. But at the surface, in topological insulator, we have conducting states, and then theta change from some value to 0 in vacuum. And then we have all the stuff. So we will be planar.
Yeah,
I see.
Yeah,
right?
It affects the boundary conditions. Well, this is what I will show to the next slides, actually.
Maybe I think like in the spirit of second volume of Landau, when you are asked to invent electrodynamics, you construct invariant objects, and this is
excluded usually.
So,
This term is excluded when you try to.
but it's allowed. You have
The principle is allowed. It's allowed, but they excluded by other arguments.
yes.
Right, not the arguments which pertain to classical electromagnetism. Oh, there is.
No, done.
Oh, it doesn't matter. That's okay. People can see. This will be most of the time covering the title of the slide. That's no. Because like you were discussing here about these boundaries, you see. Now you see. I'll show how easy this is. If you try to write, use just standard textbook things. You try to write. Those your Maxwell equations for this theory, the Maxwell Axion equations. This is your equations. This is like your D field, right? That your displacement field, and this is like your H field, right? And there's those equations which are source free; they don't change. Only the equations which are not source free will change. Now, what is interesting here in those equations, if that theta is constant, okay, if theta is constant, you can see something quite interesting. You see, imagine topological insulators, for example. Theta is pi, if time reversal invariance. If you have time reversal invariance, theta is equal to pi. The reason for that is theta comes from the flux of Berry curvature in the band structure. That's the reason. And if you have a very nice material in principle, theta is pi. I will come for that as one of the best experiments on this. It was a big challenge to make this. And now, if theta is constant, something interesting happens. Look at this. If theta is constant, this makes nothing in the field equation because theta is constant. Because of 2, div p is 0, nothing happens. So, and this is also not changing the Maxwell equations because of 1. This cancels on both sides. The only way for this to change, right? What does change here? What is going to change if in this case? Right? What is the question? The Maxwell equations don't change for theta constant. But it changes if you in the boundaries.
How it can be constant if you told me that on the surface it is defined on this surface?
Well, it's constant for the field equations, but you see if you have a surface, of course, like in the next slide.
Yeah, beyond
Theta
surface,
change.
this is 0. Beyond surface.
Yeah.
You see, for example, here.
Here is a three-dimensional divergence. Yeah.
No.
If it's infinite in size,
Yeah. What?
if it's infinite in size, if it's like three-dimensional, infinite in each axis.
Yeah. If it
then
was,
works.
then nothing happens. If I have to have a
Yeah,
region.
that's-
Here, like here, I have a region where there is theta different from 0. Here, theta equals 0. The same way as dielectric constant, right? So that constant changes on this interface. Yeah, actually, I could say, let's say like that. If I model this as a step function for that example, that would be a gradient of theta, for example, right? So that would be the boundary. But this goes to the boundary.
Yeah.
So you can solve the same Maxwell equations as before, but changing your boundary conditions. So this means because you transition, for example, here if you put a point charge outside, you have to account for the presence of this surface, right? You have to account for the presence of the surface. You know, to see how easy this is. How easy this is. This is an exercise in a textbook of electrodynamics. This is for students. This is an exercise, you see, to study Faraday Kerr rotation on topological insulators. It's a very simple exercise. The only thing you have to do is to change the boundary conditions. This exercise will solve very quickly. This exercise is super important. It's the first experimental confirmation of this axial electrodynamics in the context of topological insulators. It's related to this exercise, which the theoretical prediction comes from this paper, which is a highly technical paper, but it's a very influential paper. It's on topological field theory of time reversal invariant insulators. This is this paper. The experiment took. You need to wait several years to have the actual experiment. This is a group of Peter Armitage. And the challenge here was to make a sample, because the sample should have a perfect Dirac modes on the surface. This will have to grow by magnetic molecular beam epitaxy, a sample that puts the Fermi level at the Dirac point. You can imagine the challenge this is, because most crystals of, for example, this paper they use a bismuth selenide. In most samples people grow of bismuth selenide have the Fermi level in the bulk. The Fermi level in the bulk for the theoretical imagination was very bad for this effect.
But it is usually done with doping, but they grow
It's
the
usually
field
done.
or what?
They grow. They do the special technique. They modify the MBE technique in a way to put the Fermi level exactly because we need this to get theta equal pi, to make the prediction that the modification of the Kerr rotation, Faraday rotation of the plane of polarization. And this paper confirmed perfectly this prediction. This prediction is if you solve this exercise in Sandwell's book.
But what they confirm?
They confirm.
What do they saw?
They saw the Faraday angle, the modification, the predicted modification due to this theta term, due to Axion electrodynamics. So
So this ARPA, they checked just that this is at the Fermi level, and then they measure electrodynamics.
yeah, they measure the angle, the rotation angle of the field of polarization of light. So there is another experiment, similar experiment done with mercury telluride by Lawrence Moleckamp, but he did a little bit later. He found the same thing. Okay, they found the same thing. So this shows that that's really, in principle, it's not that complicated to do the theory, but the experiment it's very complicated. It took several years. Right? It took several years to do the experiment. I will now show some other examples that are not experimentally done, unfortunately. This is the one I predicted, which so far doesn't work. This one is based on something that happens with Axion electrodynamics, which is also very simple, extremely simple even. Imagine now I have a superconductor topological insulator structure. I have here type 2 superconductor, here topological insulator, right? So this is how imagination of the theory, that you can glue things together easily, etc. Right? Now the question is, the type 2 superconductors have vortices, right? So this is a Gauss law. Now this part is I use only Gauss law. So if I have a effective charge density that contains, if I change that first equation there in the Axion electrodynamics, it contains this term, the gradient of theta because B is 0. This was the change of the surface area, right? This is basically the boundary condition here, which is here. There's a delta function Z for this geometry that is here, right? Now, what is the total charge? The total charge is just integrate over this effective charge. And the second term is pretty easy because of the delta function. If I integrate here, so this is extremely simple exercise. I do the integral, so this B Z, if the field is the Z direction, I put Z equals 0. This means this gives only the flux, right? And the flux of what? It's a superconductor type 2. There are vortices. Right? The flux of a vortex lines, a vortex line. Here I did an example for one single vortex line. We have an array of vortices, right? So I just substitute the values here. There is one part here is the usual total charge. And then it simplifies. This gives you a fractional charge, which is induced. This result is called the Witten effect. You generate a fractional charge in the presence of, in the case of Witten effect, he was thinking about magnetic monopoles, right? But here the same effect follows from a vortex line. Exactly the same effect. So those gold points here are this induced charges, which on the surface, on the interface between the TI and the topological insulator. Yeah, why is this interesting? This is interesting because you could predict, for example, if you make now a Josephson junction instead of you put 2 superconductors, right? Yeah, so you write the standard Hamiltonian for the junction. This is the Josephson energy. This is the phase difference across the junction. Because usually what you do usually what you do is this calculation and experiment. You apply the magnetic flux parallel to the junction. So here the flux is perpendicular to the junction. Okay, that means you have to use a vertical, not horizontal junction. that's another experimental challenge that is hard, right? So most of the experiments they use are horizontal tunnel junctions. So here you have to do with a vertical junction. You apply the field perpendicular to the junction. Now this is a capacitance energy, because now if you have this point, this fractional point charge here in the interface, so the total charge is 0, of course. So you have a plus E over 4 minus E over 4, right? And then what happens, you create a capacitance here, which is unusual. The capacitance has this form because there is this extra term here that comes from the boundary conditions, from the axiom. This is the number of vortices times the fractional charge. It is delta n, it is phase difference. The phase difference, I should have put delta phi here. Delta phi is order 1, there's an uncertainty relation, as usual in the Joseph's convection. It is because of this, this capacitance will create a voltage, it will create a standard voltage because of the flux lines. You can generate an AC Joseph's effect induced by vortices only. So the thing that I will skip here, because it will be much more technical, is to show, this is in this paper that we published 10 years ago, will be that generate a new type of AC Joseph's effect. The way to measure this would be to measure the Shapiro steps. You have to measure Shapiro steps.
But if the current appears, then you have some then additional when current starts, then you have already just a distribution of the charges on the sides, and it will compensate it somehow.
Well, no, what happens, what we predicted that I'm not showing here, I can show you later, then I'll talk the paper, the actual paper, because is that there is a different quantization of the Shapiro steps. This is if you have this if you do this exactly like it's done here because of the Axion electrodynamics. That's the main prediction. This is we're not considering here usually when you do tunnel junctions involving topological insulators. What you do, people are mostly interested in Majoranas. At that time, our paper was kind of an outsider because we were not interested. We're not talking about Majoranas. We're talking about an effect of topology which was not due to Majoranas.
This is topological insulator should be quite thin. It is just like.
If you use bismuth selenide, it will be like if you use 5 quintuple layers, would be enough.
The coherence length.
Yeah,
should be.
You have to do with this to choose your superconductor or geometry such that the coherence length does well that you don't lose any tunneling, right? So if it has too thick compared to coherence length, you'll be completely lost. There is another thing that happens that we did with the same idea with the topological insulator superconductor structure. It is something that doesn't happen usually in superconductors, is that since you have this B dot B terms, since B induces E, vice versa, the momentum density, the electromagnetic momentum density is also non-zero. Even if you consider a static configuration, it's non-zero. Right? And then this leads to a non-zero angular momentum density. Right? To solve that you saw in Nasser Stock, for example, in another context. And if you integrate over this angular momentum, the total angular momentum, which here would have to include also the mechanical part due to the Cooper pairs move, right? If you calculate the total angular momentum, you get a quantizer, the fractional angular momentum here. N square. N is the vorticity, actually the vortex quantum. So this quantization is interesting because it depends. Is obtained classically, actually, semi-classically, because we're using one of the Axion term. It depends on H bar because of the fine structure constant, right? You have this fine structure constant that makes the H bar appear. There's the idea is this is a prediction that your vortex here, usually a vortex line has angular momentum 0 in conventional superconductors. But here, if you do a heterostructure with topological insulators and superconductor will have due to the interface. Yes.
May I interrupt you for a minute?
Yes.
I just forgot when was with these problems that we have not ordered the pizza, and I wanted just to ask how long you planned initial the talk.
Oh, how much time I have?
No,
I thought I have 2 hours. No,
Yeah,
thank you.
yeah, of course.
I can't.
You have 2 hours, but
No, I was.
pizza it's about half an hour, so you still have half an hour or more.
No, half an hour isn't enough.
It's enough.
It's enough.
So all people ready for pizza?
It's
Yeah? No. Okay. I just forgot.
yeah. This panel here is actually in the paper. I actually tried to improve this figure. This figure is made by your own. I told the AI yesterday, can you improve this picture? Right. So then it makes the picture completely wrong. I said, what is the island? What is the big island in the middle? Well, no, I want a picture which is more modern. I said, but it's wrong. Well, why you don't do yourself with vector graphics, then I do this, and that? Well, that's the whole purpose of you to exist, is to help me. This will not help. And then I decided to put the figure of the paper. Sorry, that's the figure of the paper, which Jeroen did in PowerPoint, actually. Yeah, he was thinking you can do artificial systems. You can create an array of Johnson surjections on the surface of a TI, which is very challenging. You have a guy, Nicola Poccia, there, who was promising to do this experiment. He never managed. And then he wanted that to measure this fractional charge. That was the idea. There was some guys in Netherlands who tried this experiment. Exactly this. Was a poor PhD student. It didn't work. It didn't work. Well, he published a paper saying that didn't work. There's a paper. Negative result is also a result. Right? That's a result. They were very nice to us, say that maybe it's because the experiment doesn't do this, and that. Things like you say when you experiment to be nice to the theoreticians. So that's a polite way to tell the theoreticians maybe our experiment is missing something. That's a polite way to tell the theoreticians that you maybe should try something else. Open a restaurant. Anyway, that was the idea. So this for the moment is still a possible experimental consequence that doesn't work. And there was other things. There's other prediction. This is more things related to angular momentum, or induced angular momentum. That is interesting. If you put a point charge outside, like this configuration, usually this problem is solved with image methods, right? That's it. Now, if you have this Axion term, the image method that you use, because the Axion term mix the electric field of the point charge generates a magnetic induction automatically. So for this problem to be solved, you have to use a magnetic point charge as well. It's not a monopole, it's a magnetic charge. This was done, people do that since ages. You can solve the magnetostatic problem in this way also. You have to put also magnetic point. There's a dielectric with this E dot B term. So this is the field that you induce, the field profile you induce on the surface that is in this paper here. And this, but this is funny enough to induce also electromagnetic angular momentum. Okay, here's the infinite plane. That's infinite slab. It's not going to to say something is moving, is rotating, is kind of crazy. But then a project for Nastya was this paper here that she talked in Lviv about in a short talk. The idea is that if you do this problem in a compact geometry, not an infinite plane, but this way, with a point charge at that distance d, you use a sphere. This is a topological dielectric sphere, right? You have a transfer of the electromagnetic angular. This will produce an electromagnetic angular momentum that will be transferred to the sphere when you change the distance from the charge to the center of the sphere. There's a problem that that's also easy to solve. What's interesting is that even without the Axion electrodynamics term, this problem would be. You say how many times you saw a textbook? You see a textbook is solved with image method for sphere. You see solutions where the sphere is conducted. A dielectric sphere, nobody does, right? Why? Because the dielectric sphere, the image charge that you put, you have to put another image charge inside, but it's not just a line of charge. From the image charge here to the center, here outside, you have to put an infinite line of charges. It's as exotic as that, but you solve the problem. In this problem, people thought they solved the first for dielectric sphere, some engineers, probably in IEEE journal in 1989. It turns out someone wrote a comment. That's an interesting historical fact. Wrote a comment saying, "Okay, this solution has been made." Remember this guy? Remember this Neumann boundary conditions from electrodynamics textbooks. This Neumann, this guy, solved the problem, exactly this problem, in 1889. Was in appendix, was not very visible because it was a German book. You can download for free from archive.org. Is a book on hydrodynamics. But then it has an appendix by solving. At that time, hydrodynamics, electrodynamics were considered. They were everything that was done in electrodynamics was inspired in 19th century by equations of hydrodynamics, right? And then they have this. He's solving exactly this problem. He has an infinite line density of charge outside. He solved exactly this problem. So it was not the first time. So, but this was in German, was hidden in the appendix. Okay, but then you can do this the same thing, but now you need also magnetic charge because you have this situation that you need you have this E dot B, this Axion term in the story. But in this process where the fields you calculate generate momentum and angular momentum, it is transferred into that's an interesting story of this paper, right? This paper here, which
Right, but
yeah.
Actually, this is what I asked Anastasia on the workshop. So it is clear for me intuitively that here should be some problems with topology in a sense that we know experimentally how it is experimentally looking on how it is realized on real crystal that you have, but this is because of crystalline lattice. That on the top surface you have one direction of this topological states.
Right. The sample is not so perfect. That's
No, I mean that either whether it is really possible to consider the sphere.
No, not a sphere, a doubt, but the point. Well, as usual, all problems you find in the textbooks right? So are in spheres, cylinders, etc. Because they know what so exactly.
I mean the states.
But the materials are not like that. And nevertheless, you still measure the effects.
I mean that in real crystals, you have on the top surfaces one direction of spins, one
exactly.
rotation like reality, on the other you have opposite.
Yes.
And they just
I know what you mean.
Yeah.
So but this is accounted for. There is you can compute having the appendix. Yes, exactly what you say. The electrons move in the surface. You have a surface Hall currents, orbital currents going on, right? And then you can see how this directions change from upper hemisphere to the lower hemisphere. Because the charge is here, there is a few lines. They'll have a surface.
It's topological state.
Yeah. You can see this. You can compute this. It is in the appendix of the paper. But what I'd like to say is that there was, Axion loop from the IFW, right? No,
I remember something, but
he tried to do an experiment. We have a paper together. It's a theoretical paper because his experiment didn't work. He wants to use ELS, electro energy loss spectroscopy, to measure the Mie scattering on this. Maybe there is a question.
No,
it's not.
high.
Huh?
Just high flyer.
Oh.
From Ale.
All right. Okay. So it's just high Flavio. Okay. Hi, Oleg. Hi. And that's then there is this. We did this paper on this Mie scattering for the sphere. This story. At that time, his group had this console subscription. Actually, Bernd bought the subscription for him because it was expensive. And then I showed this calculation to him, for example, for the plane. And then his student did with a completely irregular sample, the edge, which would be a sample. Funny enough, it's almost like it is. You see, electromagnetism is quite a robust thing. You do things sometimes. There was some deviations, of course, because of the edge of the sample, etc. But he was simulating actual samples of console.
It is robust if you consider the surface as uniform. But if this maybe can't be uniform because you can't make a surface in real life. You can't make it like monopole, magnetic monopole.
Yeah.
So you can let's say try to collect the surface from magnets from this perpendicular direction, but when you put everything, it will not be magnetic, right?
Yeah.
So it could be like this here. If you have some direction of this topological vector.
You mean for some depending on your surface.
It will not be in total.
You can have if the surface has some. That is not so perfect like this surface. Of course, you can have effects like that, but what I want to say is, for example, I give another example to defend the theory side. Take a superconductivity, right? Superconductivity, the electrodynamics of superconductors. Most applications you do is, of course, the superconductor is a crystal. There's all that, but many applications, most important applications actually comes from the electrodynamics, or classical electrodynamics of superconductor. Take the success of London theory.
No, superconductors has no direction in this sense. So, and this topological surface has direction.
Yeah, well, the superconductor you have, for example, we'll give an example now of superconductors. The axial electrodynamics of superconductors.
Do you understand your question correctly? So your question is related. What is about surface dependence of this theta term, right?
Maybe I mean.
Flavio, could you answer mathematically?
But
what is the value of theta
the value of
at surface?
Yes.
So is it constant?
Yeah.
Ideally, if you have ideal is constant. It's constant always. It could not be pi. If you have this pi, is another story. But that's the main challenge. If you want to do the exactly like time reversal invariance preserve, that should be pi. But usually it's constant because it comes from calculation People actually calculated that with DFT.
But then this effect will be robust because
Yeah.
it's theta is even approximately constant. Then everything.
Yeah,
is fine.
people calculate. They do DFT. The DFT, they calculate. Can take any model, but for a tight binding model, because this theta is just a flux in momentum space of the Berry curvature of the band structure. That's what it is. Nothing more. That's people actually calculated that. That was those the first papers already calculated that they use they do a calculation, they get a constant value, right? That's okay.
Just to clarify this picture, is it correct actually that we know that angular momentum is conserved, right?
Yes.
So you said as soon as we move this charge up or down, this sphere will rotate. So
Yeah.
this means that actually there is counter contribution
Yes.
related to electromagnetic field, right?
Exactly.
Okay.
And
Exactly.
also, the field of the charge may be small, so how could we observe the
Oh, yeah.
angular momentum transferred
That's
to
a very
sphere?
good question that you answer.
Will it be a strain field, or will the sphere itself as a rigid body?
Well, think this as think about you have a stem tip or something, right? So where you have a charge there, but the charge can be that's an interesting question, because if you compute, if it was a point charge just on one electrode, this doesn't matter. That's in fact is super small, because it depends on the final structure constant square. The difference between such an effect and this first experiment I showed you, the Faraday curve rotation, is that this is the correction is linear in alpha. Alpha is 1/137, but alpha square is 10 to -7 or something like that, right? So alpha square is too small, but you can compensate that if you have a charge probe which is large enough. You can have a large number of units of charge. This is actually calculated this example, so that you can have this point charge. You can make as large as you want. With the Faraday experiment is because it's not a charge, is light that we're shining on the surface. This is the boundary condition just gives a correction linear in alpha. This is experimental bridge. But here you have to make sure that your tip is, for example, another question, for example, about the vortices that I mentioned earlier, right? I said that how I can measure the fractional charges of the vortices on the surface, right? I have to take STM or some STM tip and see if I get a response, right? So this is you have to make sure that your charge probe is large enough to react. That is the main point, because many of those calculations in Axion electrodynamics have start sometimes in alpha square, which is simply too small, right? Let me go to
By the way, did you play with Kepler orbits? It's actually just suggests stellar dynamics, yeah, classical mechanics.
So let's I don't know. Well, you can, that's a fascinating topic, but you can do it's you can do actually this topic now, talking about this, not about Kepler, but about astrophysics in general. You were contacted by astrophysicists when you wrote to this next thing, when you take various metals. Was two last papers of Vera's thesis. This is actually her slides, this part, you see. It is a case where theta is not constant. In various sand metals, actually theta is much more, this is here is much closer to what they call chironomy, right? So in high energy physics. This theta, you have, oh, this is one thing I wanted to show in this talk here. I forgot to add a slide about this Axion term, the high energy physics. Unfortunately, I forgot to put this. I was thinking the train about this. And then I forgot that I wanted to put this slide, because the slide is beautiful. There is this paper by Nielsen Ninomiya, 1983. right? That colleagues of Bogoliub Institute surely know. This is about putting neutrinos on the lattice. That was the idea in 1983, right? They thought neutrinos are massless. Then they have these pictures. Those pictures you see nowadays, in 21st century, in papers of various metals, they have exactly the same things. The fermions in the bulk, the Dirac cones, they merge in the bulk. Oops, that is that's the drawback. It was laser would not happen, but there is this exactly the same picture. They put the bulk here. They put the bulk here. So those pictures you see, modern papers, they had all of this more than 40 years ago. Now, then the beautiful thing in that paper, he has this anomalies, which he talks about at the end of the paper. He mentions semiconductors. You know, one material, what will be in solid state physics? That's an incredible thing in the paper. Solid state physics, you know which material he mentioned? Mercury telluride. The first of all, he mentioned mercury telluride. I have a theory this guy he was trapped in the past and came from the future. Got trapped in the past because that cannot be, right? That's exactly that material. So but the main point of the paper, that the paper is very influential in the biosand metal community. They all knew that paper. They all knew that paper. In biosand metals, these things have the following. It's not like a plane wave, this theta, right? So that's not. It's B dot R, and B is this distance between the via cones, and B naught is the distance in energy. And there are two possible effects here, and I have a cutoff for the pizza. That's good. There are two effects here. So the first effect is if I don't have this term. If I don't have this term, this B, what you have a situation with time reverse invariant, because I can change T, the B change of time reversal. This doesn't change, and this leads to something. It leads to current, to a current which is proportional to magnetic induction. And this will the high energy literature also in condensed matter nowadays follow a chiral magnetic effect, because this B will cause things to rotate inside this. Well, we'll see an example of that in one slide or two later. Because it's quite unusual. Usually current, think about it. Current is superconductor. It's proportional to vector potential. Right? When in the London theory, for example. Here is proportional to B. Right, so that's the thing. And now, if on the other hand, if you allow for breaking a time reversal symmetry, you don't have this term, and then this you can derive the current associated to this. This is an almost Hall current, so it's a B cross E term, right? This is more easy experimental than the first one, but what we consider with Vera in 2024, there were two papers, very similar papers. They were published almost practically at the same time by Hansel, Wurczak, Stavhammer, which here it has a shady story. This one is a Russian woman. Turns out she was a spy. Seriously. She was a spy. She was deported for Sweden. Vera cursed her. Because they were doing exactly the same calculation she was doing. So she got deported for Sweden. Yeah. The question is, now imagine if you do London theory. That is still very classical, okay? But if you look at this term, right? There's only the time direction. This looks like a Chern-Simons term. That's A cross. It's A dot cross because of this absolute cross rotational of A dot rotation of A. But it's in space only. It's in space only. And here there's the usual terms you find in London theory, except that you have a phase here because it was considered the vortices. But otherwise, if you ignore the phase, if you get the phase away, what we get here is a London theory. London theory really from 1940s, 30s, really very old stuff. But with an additional piece of term that comes from the Weyl superconductor, right? From the time reversing Weyl superconductor in this case. Now, what is interesting here that I will show that you think is easier to show this part first, because it's a slab solution. Because the first thing that London does in his textbook is to solve a problem for a slab, right? To take a slab to demonstrate the Meissner effect. What's the Meissner effect? There is a London shows that it's not completely zero. There is a penetration depth on the surface. It decays exponentially, right? You put the magnetic field applied parallel to the surface. It's very easy to solve with the boundary conditions. You'll see that it decays. It decays why? Because of this. This is without this term. This term is the term that comes from Weyl fact, from the Weyl fact, right? London theory is only this plus this. Apply a field, and there is a slab. That's it. Now, what does this term do? That's the question. First, you see there are not only one equation any longer, like in London paper, now we have to consider two equations, because there is a curl of B, right? So these two fields appear, there's a By, Bz. Now we have two fields. Now you see that what chirality, chiral magnetic effect means with this thing. You introduce here a parameter which is related to this coefficient of the theta here, which is somewhere. Okay, I lost it. Oh, it's A here. It's Q B naught over pi. Q squared B. Q is the charge of Cooper president in this case, this contest. So what happens is that if you solve this equation, there are two different regimes that happen. One is for A smaller than A critical. This M here is the inverse of penetration depth. Is A greater or equal A critical. A critical is given by 2 divided by penetration depth, 2 times M. Right? Now, what are these two regimes? These two regimes, I just said that there are two regimes, but I don't know what, I didn't say you what they mean. Right? What they mean is the following. This is the exact solution, the London case. That's the exact solution. The exact solution, this is a B applied, there's a B of X, right? And then here there's this, some of the signs. You'll see everywhere there's a square root of A squared minus AC squared. Then you can see why there are two regimes, because of course the square root will change if this argument is positive, it's trigonometric function, but if the argument is negative, there is an I, it would be a sine hyperbolic.
Sorry, I missed it. What is it U hat?
U hat is this. Yeah, it comes this U hat is very important because the unit vector that rotates inside the sample. When you solve those two equations, right, you have two fields. In London case, if you take this equal to 0, that's one thing you will have is a decay here, only one component of the field, right? But now we have these two components. What happens inside the sample is there is a plane, By, Bz. A field is in the plane, it rotates inside the sample, right? I don't have a three-dimensional picture of that, but we put this unit vectors with spatial rotations. There's spatial rotations, see? It's rotating inside the sample. Here is for a small relative to AC. You see what happens here. There is this blue lines here are By. If the yellow is Bz, right? And then you have you see that this is the case while Vy decays like exactly like you expect from London theory, right? Exponential on both sides of the sample, the Bz first go up, it then goes to zero. There is a small bump here on both sides. But here it goes a little bit negative and then goes up. But then the Meissner effect is a little bit weird, right? It becomes weird. It becomes even weirder if we start to increase even more this parameter A, right? So now the bumps are larger. Also here the blue, start the blue part, which is the By, it starts to look less also like London. It decays, but then goes to a minimum and then it goes up, right? And then now even bigger, almost equals to a critical, you start to see more oscillations inside, spatial oscillations inside that sample. You then you start to see, okay, is this doesn't look any longer like a typical Meissner effect, right? Because there's the Meissner effect, we all understand that the field should vanish exponentially inside the superconductor near the surface. Now here it's start to be above AC. If you are above AC, then it's basically things become a mess. The field will start to rotate widely. There's this now you can wonder, is this a Meissner effect? No, because Meissner effect, if you take the standard definition of Meissner effect, is zero.
But what about current?
The current, there is a current, which I removed from the slide. But there is a current because I didn't want to. I was this is my only prediction that apparently will work. I was predicting the pizza. Then I removed from the slide this current, but there is a current. The original slides, there is a current that rotates also. The current.
So it behaves like BZ or what?
Well, because you see, remember that the current, there is a component that's proportional to B, right? And then there is a part that behaves like this By and then Bz. But there is a correction to that, right? But unfortunately, we have plots expression, but I removed it for time's sake. But like if
it should go like.
But it should do like this.
Like yellow, right?
Yeah, yeah,
It's like
yeah.
curls.
Yeah, usually the current is in the other direction, the usual London theory, but here there are here there are again two components of the current, right? There are two components, right, Vera? You remember the expression? You defined that this is not long ago, it's just 1 year ago. Huh?
It's also Y and Z components, and it has the same like decay function basically inside the sample.
Yeah. Okay, that's thank you for the answer.
Sharing the blame.
Sharing the blame. I'm sharing the blame with you. No, I removed I saw that I removed the slide. Maybe it's there. No, it's not there. Oh, there is. But now, yeah, it's not there. Right. Anyway, the total current is like this. Oh, maybe I have the current. Maybe I didn't remove. Let's see. Maybe it's there. Total current contains a superconducting current, but plus this thing, right? Plus this part. The obvious, I should just show that this rotates, right? You can see what the current is because of this, right? So this current should be given a still by Ampere law. I have no time dependence in this problem. So the current is just the chiromagnetic effect part plus the usual London superconductor. Unfortunately, I don't have the current. Okay. I jump to the vortex part. This is a single vortex solution, same problem. A single vortex solution. How much minutes negative I am? Negative minutes. I don't know. I already negative. I'm pretty sure about that. I 15 minutes over the.
There's still no pizza.
Pizza is not arrived yet.
Huh?
Pizza is not arrived.
Pizza didn't arrive.
You would smell it.
Yeah, but maybe the guys outside was waiting for me to finish.
No,
No.
Yeah?
it's not.
Okay, the point.
Busy eating pizza, right?
The point here, if you look at this, is an exact vortex solution from the London, exact in terms of London, right? So it's a single vortex. You still see that there is this Bessel function K naught, like in the usual vortex solution, but with the difference that you have again to write the two chiralities, if you want, plus and minus of the associated to the magnetic field. And here again appears this square root. If I not here is the elementary flux quantum. Okay. Now, interest is this mass here, this mass, this London mass that appears here. Because usually what you have is R over penetration depth. M is usually is 1 over penetration, London penetration. But now it's a complex value. Now this is a complex value. The whole thing is real, of course, because you add the both conjugated M's, right? And then it is significant here because first thing you see for A smaller than AC, those oscillations, you can start to see those oscillations appearing just like in the slab geometry around the vortex. So the vortex is at the origin here, but you have also those spatial oscillations of the field. Now the question you can ask, what happens when A equals AC? Because when A equals AC, this is because purely imaginary, right? If this was the Bessel function I or the Bessel function J, I never remember which one is there is modified. This is a modified Bessel function of I don't know, the usual Bessel function J.
Imaginary argument. This is K.
Yeah,
This is K, imaginary Bessel function modified.
Yeah, but this doesn't have this is not defined for this one. For the I and the J, it is, but for this one, it ceases to be defined. That's the point. Then you lose the vortex solution. Here's you see, before you go to that, that's the water component, because I mentioned to you in the slab geometry that there is two components. First, the BZ component, which is the usual one for the along the vortex line, right? Along the vortex line. And there is a component which you don't have if you don't have the chiromagnetic effect, which is the phi direction, cylindrical coordinates. So it's also that's two chiralities, right? But here is the Bessel function K1. That's the Bessel function K1.
Now we are at T0.
That's
No,
it's a-
zero, right.
that's
And when AC is zero, it is zero. It would
no, AC zero is when the penetration depth is infinite, right? So then you are normal state. Yeah. You have those oscillations also for this okay, here are both solutions again. The question is whether this works for A greater than AC, and the point is that it breaks down already at AC because right? That's what I remember, right? That if you correct me if I say some nonsense. I'm pretty sure I say nonsense. You're just being nice to me. But anyway, so there is this for A above or equal to AC. There is no vortex solution. You have perfect diamagnetism, just like in ordinary London theory. Okay, so that's this because this Bessel function K cannot be defined by pure imaginary coupling. Right, so that's this. I hopefully I concluded my talk. This is the conclusion is very simple. So Axion electrodynamics occur in many interesting materials, especially the topological ones, as what people find more interesting, but not only in the topological ones. Unfortunately, many predictions resisted. I didn't exhaust all predictions here. Okay, there are much more predictions. I would be talking the whole day. Then I will have lots of
Олена Миколаївна.
ex-friends.
Мені потрібно.
You see, then I don't want that, so then
Ну ладно, я перезвоню.
Then,
Дякую, да.
but there are problems with
Да, да, я
experimental
віддав,
design,
правильно.
many challenges, right?
Добре,
I always say,
да, да.
theory,
Я
I always say to the students
Добре, да, дякую.
who seem to be struggling, right? The students who seem to be struggling think that theoretical physics is difficult. I say, theoretical physics is super easy. Experimental physics is complicated. It's super easy. If your problem doesn't work, you just invent a new one. You don't need a new sample, don't need anything. You just invent a new one. You just take your pen, you do a new one. You change the problem. How many times we did that, Vera? That you change the problem, right?
Let's discuss that.
Yeah, it's true. Change the problem. So,
I have a joke about, I know, remind me later.
yeah, well, it is true. It's true. So the problem with all these things, let's say you have to tell. So you see the example here. So Sasha reminded me that how the samples are, how the actual samples are, right? So that's it. You guys are crazy. So. So that's difficult. Right? That's why I say that that's a way I make the students more optimistic of the future. Thank you very much.
How often you communicate with experimentalists who do Josephson junctions?
Look, the first thing I did, I was communicating with Joseph Dufouleur. Joseph Dufouleur of the IFW, who's got more recently involved with the platinum bismuth too. Actually, he was the first guy who thought about that, but before Artus comes in the game. Joseph was supposed to do those samples, but he was interested mostly in Majorana, so you don't talk to him. Talked to several people, but they never did. So I think I don't know why. When we call a Pocha, we have even a DFG proposal together. He got the money. At that time, for his proposal was with bismuth telluride, the antiferromagnetic topological insulator. You had different predictions there. He wanted to use. He got the flakes for Ana Isaeva. He got the flakes. He had everything. He tried to do. He didn't. And then he started to twist Bisco instead of doing that. And then he went to something else. So the problem is that you have to. I don't know if it's only luck with the experiment, or that things should work immediately, or whether I should go more to IFF to disturb them. Hey, I'm here. So I'm Axion loop. With Axion loop, the main challenge was for this ill spectroscopy. It was the equipment. The equipment was being upgraded, and then they start to do other things. There is something like that.
I just don't know what they are doing actually, and what is the level. I never communicated this stuff. We just saw like a clean room and so that in principle.
Yeah.
I just even don't know whether they can make a Josephson junction at this board.
Oh, they can. Joseph Dufouleur. I always joke with him. You don't want to do the Joseph effect. That's Joseph he's doing junctions all the time, but
I mean, maybe it would be useful if you try to join them and to try to make Josephson junction by yourself, and then you understand.
For myself, yeah.
Then you maybe understand which suggestions you will do some predictions when you do the junction.
Look, if Nicola Pocha, for example, the first thing that happens when I enter his lab, he says, "Flavio, don't touch anything." He says, they have the idea. Don't touch. No, Joseph. Nicola, let me look at this. No, go away. You see, you will break this. This is expensive. So don't touch my glove box.
Let's make it about the question.
Yeah.
One more. Mathematical question is like where you come to critical value of AC with the solution in the previous.
With this lab?
Yes. The last case when you A is above the critical A, above the AC, we can see an oscillation. But if you come to the critical value 0.95, follows from solutions that we come to hyperbolic functions.
Yeah. Well,
we cannot change sign to hyperbolic functions, and it seems in this case we cannot find an oscillating solutions.
well, the oscillator comes from this rotating here.
From the
From the unit vector, the vortex.
Yeah.
Actually, I forgot to mention. I want to mention things about. I come to the astrophysics guys who contacted us, because the funny thing, you think, okay, I will Google Scholar, you find what is done, etc. And then of course, so your search depends on the keywords you know, right? And then I use the keywords I know, right? And then I didn't find anything. Then the Japanese astrophysicist, theoretical astrophysicist, contacted us. Oh, we cited his paper actually. Oh, what happens when you have the time, because there is the chiroplasma instability. There was things about the stars. And then you realize that they were solving exactly the same equations you do here, but they're completely different words. Completely, they were using Laplace, Beltrami, fields, etc.
No, it's known, force-free electrodynamics. This is what they call it. It's actually in real corona, in solar corona. That's correct.
Yeah, but I didn't know that.
No, it's the famous Laplace-Beltrami equation.
Yeah, Laplace-Beltrami.
And by the way, it seems it was Naoki Yamamoto, right?
Yeah,
that guy.
Yamamoto. This guy contacted us. You see, if I was talking to you, I would know about these guys. But I was not thinking about it. But I was interested in overlap with that, because he has exactly the same equations as including this mass term, capital M square B. Look, it was really interesting. But he was never talking about Meissner, nothing about this. This was what the interest. So,
yeah, I have two short questions. First one is very naive, perhaps, and so like I didn't see it directly from the Lagrangian, but in the classical superconductor picture, we can invoke the Higgs mechanism for the for the photon field that sort of acquires a mass and whatnot, and this is related to the Meissner effect.
Yes.
But here, the magnetic field does not vanish, and I was wondering, like in the same picture, thinking along the same lines, like what would happen to the mass term? Would it like arise before the photon field terms? And
no. Actually, the mass that's exactly the Higgs mechanism. The London theory is in disguise, but the Landau theory, which is a further generalization from London theory, is the Higgs. Is basically the Higgs model. If you solve those equations, including the order parameter, in this case, you can find the profiles of the field, and you will find that there is this exponential decay. The field, the contribution of London, he also gives Landau, is that the field decays exponentially close to the surface. It becomes zero because of that. It's a smooth process. It's decaying rapidly, right? That's the Meissner electrodynamics, Meissner effect, which is just the photon getting a mass, right? The Higgs mechanism was Higgs mentioned actually in his Nobel Prize paper. That is the example of superconductors, right? So that's the answer, I believe, that Yeah, if this is the question.
Yeah,
Yeah, you said you have a second question.
yeah, second, very short and very whimsical, perhaps. Like, so you mentioned the CP problem, and
Mhm.
I was wondering, like, did people ever think of that? Like, if we had that term,
Mhm.
E dot product be sort of it's analog, right? In the standard modern Lagrangian or whatever. Like, and then we have this link between angular momentum and the electric field.
Mhm.
Like, would that imply that the universe spins or whatever?
Oh, I know, but that would be a long shot. I don't know. That's well, what we're doing there, we're not thinking of, as far as I can tell, not about relating the universe. That because there it starts to, if you think about that modifications of electrodynamics due to the anomalies, etc., plus the universe, you have to include other effects, of course, because there are universals. There is gravitation. Gravitation should play a role. Actually, one thing, if you want something very exotic in your mind about this, about electrodynamics and gravitation, you see, I already said this judgmental thing from Vera, but if you want to do something like that, to think about something like that, you can. There was a very interesting idea about from John Archibald Wheeler, which was abandoned for other reasons, which is better to have in vacuum. As in vacuum, there is our electromagnetic field. There is no matter, right? We know that matter is what creates the source of gravitation, right? Now, what he was telling you, it's okay, but imagine if the space is not topologically trivial, space-time, right? It contains handles like a donut. Or like where is the you're like this? Imagine it as like this. Where is this? Space. Imagine it as in 4 dimensions, okay? But that's more than 4 dimensions. Then you have this thing here. This then a magnetic field. The magnetic field will have to follow here, because this is the space-time. It goes through this electric field or magnetic field. This will create a flux. If you enter 0 in this throat to live on that side, it does create a flux. The interesting, there is a mathematical theorem. That's a mathematical theorem that this flux is quantized. He was using this to say actually matter is a kind of an illusion. Is actually the electron, when you see the quantization of charge, is just this thing going out of a it's like a. He was thinking about wormholes. Okay, he was thinking about wormholes. This particles, he gave a name. The name was geon for geometry. On because it's a particle, geons. Then this was there were people who considered this it not be in this context, etc. But it's an intriguing thing that matter will come from the topological properties of non-trivial topology of space-time. Right, so that will be something more exotic if you call it gravitation. Right? Other questions?
Also,
I think it has a.
yeah, when you derived the chiral current for the Weyl semi-metals, so I saw you needed there. Well, it seemed to me inhomogeneity of in real space of the semi-metal, so that the separation varies in real space. Yes.
No, which separation would be this distance?
Separation is in momentum space, but it seems that it must vary in material in real space.
No, what do you mean? B is constant.
B is constant, but
theta is not. Theta is not.
Yeah, theta is not constant.
Yeah, but B is constant. Yeah,
this is constant. The values are not there. So that's the
Some question?
Why electromagnetic field essential for main for most jump from?
the strong, well, don't need, but the problem is what is the resolution of your experiment, right? So if you have, yeah, the question you can make, you can think, you can detect things. The worst thing is not the strength of the fields they use, if they are external fields, right? So there is always a part that is induced by the dynamics of the system, but the whole problem for comparing to experiments, anything is the size of the fine structure constant. Right, you have to have experimental things that are because, as I said, there are many things that you can predict as a theoretician, right? That are completely nonsense because it's so tiny that nobody will see. The problem here for us that the prediction involving Axion electrodynamics is less the strength of the fields involved, but more the size of the fine structure constant. If you have an effect that's proportional to alpha square, it's tiny. It's tiny. Then you can think, okay, then I use a larger field or more or a huge electric charge, which is not difficult to have. Any piece of anything will contain lots of electric charge. Think about it, right? But that's the main limitation for some theoretical predictions, you have to have an experiment that's sensitive enough to detect. This is the part with not easy.
How's it possible 24 of 18 is not?
Oh, it's possible. This I was always wondering. You know why it's possible? Because I didn't do this template. This is a template for FW. And then when I look at everywhere in PowerPoint where to change that, there is certainly a way to do this in PowerPoint, but I don't know. And then apparently the FW, people in the FW, I don't know who did this template, decide that must be a cutoff. Let's put 18. Nobody talks more than 18 slides. And that's why I did more than... This is something that always a problem, at least in my presentation. There is this...
Okay, no more questions. I think people are ready for pizza.
Ready for pizza. Thank you very much.